Muito bem, boa tarde. Hoje eu tenho o prazer de apresentar para vocês Tim Griffin, certo? Que tem um histórico interessante. Ele recebeu, na graduação ele estudou matemática, depois fez doutorado na Universidade de Wisconsin, certo? E ele passou um tempo aqui no Brasil conosco, no então Departamento de Ciência da Computação. O Instituto não existia. Isso foi nos anos 1989 até 1991, não é isso?
Sim.
Certo. E atualmente ele está no Department of Computer Science and Technology da Universidade de Cambridge. Bom, vai falar sobre esse assunto. Por favor.
Muito obrigado. Eu estou muito feliz de visitar a UNICAMP de novo. É muito legal ficar aqui e ver todo mundo. Eu vou dar esta palestra em inglês porque eu não sei discutir os detalhes técnicos em português. Tudo bem? Não vai ser problema? Espero que sim. Bom, primeiro eu tenho prova que eu passei aqui. Sou eu, 1990, e não foi eu que fiz a pichação lá, não, mas foi. E eu tenho mais uma foto de mim trabalhando com os alunos. E isso eu acho que foi tipo workshop, alguma coisa assim. Não, olha o respeito que eu estava recebendo deles. Eu fui chamado professor Chin Chin na época. Então.
Qual deles é você?
Então. Eu aqui. Tudo bem. Então, vou mudar para inglês agora. Okay, so I think, is this too loud? No, it's okay. I'll put it down here. How's that? Better? Okay, it's okay with you? Okay. So the thing is, we learn as undergraduates, we learn about shortest paths in a graph. Okay, so we learn in algorithms. Typically, we learn Dijkstra's algorithm, Bellman-Ford, Warshall's algorithm, things like that. That's one of the first things we learn, right? So we have some matrix, let's say, or representing a graph with weights on the arcs, and that's sort of the problem statement. And the solution we want in the shortest path case is the set of a matrix containing the set of best distances, the shortest paths, or the distance of the shortest path. So, for example, here the distance from node 1 to node 4 is a distance 5. That's the best we can do in this graph. And so the thing is to think about this problem algebraically. What problem are we trying to solve? We're trying to take that adjacency matrix and turn it into something I'll call A star, which is the minimum over all paths from I to j. The ijth entry in A star is the minimum over all paths from I to j. And then what we do is we sum up the weights on the. We use addition to sum the weights in the path. Okay, so that's something we all are very familiar with. And I'm calling it global optima here because we're going to try to find the shortest paths over all possible paths in the graph. Okay, so that's something we all know and love. But what was discovered, people started noticing back in the 60s, 1960s, 70s, mostly in the operations research community, people were coming up with different algorithms for, like, let's say here we have the same graph, but I'm going to interpret these weights differently. I'm going to interpret them as a capacity. Okay, and so instead of summing up the weights along a path, I'm going to take the minimum weight on the path, which represents the bottleneck link. And then I'm going to take the maximum over all such path weights. And so then I'm going to be able to calculate the sort of the highest capacity paths in the network. And so people notice that, you know, I've replaced min by max, and I've replaced addition, I've replaced plus by min. Okay, and I can still define the same problem. You know, the problem I'm trying to solve is that problem of A star, where now I've just replaced, I've replaced min by max and plus by min. But it turns out that people started noticing, well, they came up with algorithms to solve this problem. Okay, and then people said, oh, that's just Dijkstra's algorithm with, you know, those operations replaced. Oh, that's just Warshall's algorithm, where you've replaced min by max and plus by min. And so they started to realize, oh, wait a minute, there's a generalization here. There's a whole family of algebraic structures that these algorithms, Dijkstra's algorithm, Warshall's algorithm, they work. Let me just give you an example of a slightly strange one. Maybe you haven't seen this kind of thing. Now we're going to replace, let's say, thinking about shortest paths, we're going to replace min by union and addition by intersection. And instead of putting integer weights on the links, we're going to put little sets there. And you can think about these as sort of attributes that those arcs might have. You know, so this is saying that this arc from 1 to 4 has attribute A and attribute B. Okay, and if you turn the crank, you know, turning the crank means compute that A star, then it turns out that, well, for any x in this set, if x is in the solution from I to j, that means there's at least one path from I to j with x in every arc along the path. So you can think about that as you know, you only want paths that, let's say you want to select paths that have a certain attribute. You know, let's say, you know, the path from 4 to 1 has these two attributes because every arc along the way, there is a path where every arc along the way has those two attributes. So, okay, so it turns out you can use Bellman-Ford to compute this. Just replace min by union and plus by intersection, and boom, Bellman-Ford works. Dijkstra doesn't work for this because Dijkstra algorithm requires a total order, and this only has a partial order. It's essentially subset containment is the order related to this thing, and so Dijkstra's algorithm doesn't work for this. Okay, so again, this is maybe late 60s. People in the operations research community said, hey, you know, all of these things fit this pattern, this formalization called a semiring. How many people have heard of semirings? Okay, one. So a semiring is like a ring, but the additive part is not a group. It's a semigroup. It doesn't have an inverse. Okay, necessarily. It might have an inverse, but for our purposes, the additive component has an identity element, 0, I'm going to call it in this case. So for example, for min plus, the shortest paths, 0 is infinity, of course. And the additive, the multiplicative component here is in shortest paths is plus, and the identity, the 1, is of course 0. Right? But the reason for this notation is just a generalization of the algebraic structure, the real numbers with plus and times that we use to do linear algebra. And it turns out that this sort of algebraic approach to path problems uses a lot of sort of linear algebra, but not with real numbers, with semirings, sort of linear algebra analogs in the semiring world. For example, matrix multiplication can be defined and things like that. So if you look at this theory about finding paths, these two rules, distributivity of multiplication through addition, are, if you look at the theory, these things are critical for the classical theory of semiring path problems. I'll talk a little bit more about those rules later, but so we'll just look at a few examples. For example, here are the examples that I gave before in the semiring notation. Here's the additive component and the multiplicative component in the different examples that I gave you. These are special kinds of semirings that I'll call path algebras because they're especially nice for computing paths and graphs, because it turns out that the multiplication is commutative, the addition is idempotent, which is going to mean that there's a partial order defined on the paths, and this is just a technical detail that's important for something I'll talk about later, and this is just saying that one is also an annihilator for addition. But it's a detail that I'm not going to get into in a big way now. But what's nice about the semirings is, again, like I said, we can define addition and multiplication on matrices just like we do in linear algebra. Except, of course, we're using this generic kind of abstract plus and abstract times. As long as these rules especially hold, then the matrices themselves become a semiring. The square matrices, at least, become a semiring. And that helps a lot in the theory that we can develop. So how to compute that A star? Remember, I talked about A star as being the solution. One way to do it is just, well, I there, we take I, which is the multiplicative identity matrix, and we just add it to the adjacency matrix, and we take the, if this is a path algebra, we take the n minus first power matrix multiplication. And this is especially true for path algebras. The reason we get that n minus 1 is because essentially that funny rule here basically says you can't go around a path. You can't go around a cycle. It doesn't. I mean, some algebras, some semirings, you can go around the cycle multiple times. But with path algebras, you can't go around a cycle. So this is important. We say, how do we compute this? Well, one method is just matrix iteration. You multiply, iterate the matrix. Of course, there are more efficient things, like more efficient algorithms like Dijkstra's algorithm, which can compute one row of A star at a time. Typically, you would with an n by n matrix, you would run Dijkstra n times to compute A star. It might be more efficient, especially if you have a sparse graph. So this is the basic idea. We also have, with path algebras, this is a well-defined partial order, and that's the order that we're actually minimizing when we're trying to find best paths. Okay? So that's kind of the classic theory that has been well developed over the past, let's say, 50 years. There are lots of literature on semirings. I'm going to focus on pathfinding in graphs, but semirings have been used in all kinds of applications, in natural language parsing, for example. They're used in modeling discrete event systems. They're used all over the place in computer science and operations research. This book is a good introduction because it doesn't have a lot of theorems and proofs in it. It has a lot of examples. This book is kind of an encyclopedic book with lots of proofs and very few examples. But it's from some of the two authors there are some people from the operations research community that really developed this theory back in the 70s and 80s and 90s. Okay, so if you're interested in exploring this more, I recommend this. So that's kind of just the background of where we really started this work. And let me just skip a little bit. I want to look again at distributivity. So I'm going to think about distributivity in terms of a distributed, let's say we're computing paths in a distributed manner. and I'm sitting at node I there, and my neighbor is at node J, and I have this link weight A that's connecting my neighbor, and my neighbor has 2 paths. With these paths could be multiple hops. One has weight B and one has weight C. How do I interpret this distributivity rule here? Well, it says I can think of this one. I can think of plus as like a choice operation, like min, right? So my neighbor, who's making that choice? Well, it's my neighbor J. Makes a choice between B and C, and then I apply I'll think of this as my policy or whatever. I apply my weight A to that. And over here, I have something different. This is full global knowledge. I can see the paths. I can see both paths. The one A, then followed by B. I can see A followed by C, and I make the choice. So this is saying that if J makes the choice and I makes the choice, same thing, same difference. And if you look at the theory based on these books, they're all the theory really is dependent on distributivity. So what we're going to do new here is we're going to throw away distributivity and see what we can still compute. Why would we do such a thing? Well, this started back maybe in 1998, 99 when I was at Bell Laboratories. And I started looking at this strange routing protocol called the Border Gateway Protocol. So the internet had just been commercialized and it started growing. And this protocol was there and nobody really understood it very well because it had grown organically. And people just kind of hacked on it, right? And extended it as internet service providers requested changes and things like that. And so it just evolved into this thing that nobody really understood. And I worked with some folks at Bell Labs, Bruce Shepard and Gordon Wilfong, and we started building models of this protocol, trying to prove some theorems about it. And so the first thing we did was we tried to sort of come up with a model that was, you could explain in 1 page. Just like you can explain shortest paths in 1 page. Because the problem with this protocol is a very complicated protocol. The protocol is complicated, the way people use it is complicated, so we wanted to sort of kind of distill that into a really simple mathematical model and prove some things about that model. The reason we're doing that is because at the time people were noticing all sorts of very weird anomalous behavior of this protocol. So for example, the protocol is not even guaranteed to converge. And it's a distributed Bellman-Ford computation. So that means you just sort of look at what your neighbors have. You don't have global knowledge of all the topology of the network. You just know what the best routes of your neighbors are. They tell you. And then you compute your best routes based on the best routes of your neighbors. Okay, and so this protocol was doing weird things like not converging in some locations. It was having strange multiple stable points, multiple solutions, and a lot of them were interpreted to be incompatible with the policies that the weights that people were putting on the links. They didn't make any sense. And so we were trying to build a model to kind of make sense of this, okay? Because we would go to the people at Cisco and say, what problem is this protocol solving? And they would say, well, you build this message and you do this and you run this algorithm and you pass the results to your neighbors and then eventually things converge, and that's the problem we're solving here. Okay, so I think the first thing we did is of interest is we started thinking, wait a minute, let's ignore the distributed nature of this computation. Let's just think about it as a static problem. And we started thinking about it as a solution to a matrix problem. Okay, so BGP, this distributed protocol, is trying to compute essentially a solution to a matrix equation. And that's when we started modeling it. And so in the semiring world, the same thing is true. A star is a solution to these matrix equations. I'll call them the left and the right matrix equation. And this kind of iteration of this is the iteration of the left equation. You just start with the identity matrix and you iterate that equation we know that we only have to iterate this equation n minus 1 times in the semiring world, and it converges. This is a good sort of high-level mathematical model of distributed Bellman-Ford. You do the best thing you can do given what your neighbors have given you. I mean, that's actually what's going on here. At each iteration, you just look at your neighbors, you take the best thing. And so this was our model, to forget all the complexity of this protocol. Okay, we're just going to solve a matrix equation. The problem is that it's not, the distributivity rules don't hold in the BGP world for good reasons. Okay? So what are the good reasons? Well, here's just one example of why distributivity, this algebraic notion of distributivity, doesn't hold. Here I am, a provider, let's say J is a provider like British Telecom or AT&T or Sprint or France Telecom. They have two paths, multiple hop, let's say. One, a short path through a competitor, a shorter path to this customer through a competitor, let's say AT&T. So let's say the J is AT&T and the path through the competitor is British Telecom. Okay, and then there's another longer path through a customer to that D, that destination D. Well, it turns out that normally, given normal contracts between customers and providers, the provider will always prefer that longest path through a customer because the customer is paying, right? And, if the customer comes to the provider and says, hey, there's something wrong with my routing, can you fix it? And they say, well, I'm not even using your route. I'm using my competitor's route. The customer will say, well, what am I paying for you? Or what am I paying you for exactly? I'm paying you to provide me this service, so you better be using the route that I'm giving you. So that guy is taking that longer path rather than the shorter path. But here's the customer. Let's say I'm the customer sitting here. I look up at that provider, and I see two provider routes. I pay for them both. To me, they look the same, except one's longer than the other. So I'm going to take the shorter one. Okay? So this is a disagreement. I mean, this is where the kind of place where distributivity just falls apart. In other words, we don't agree on the paths. Okay? And this is just the simplest example that arises in interdomain routing. You can imagine the policies are all based on contracts. There's no sensible notion of global optimality in this world. I mean, how can you get China Telecom and AT&T to agree on what are globally best routes? Depends on their interests, right, and their relationships to other networks and things. So there is no notion of global optimality here. So what we are saying here now is, okay, so this is what's new about what we've done. We're going to say, okay, if you have distributivity, great. A star and left and right solutions, they're the same. Great. But without distributivity, maybe they're different. Maybe we can compute A star, maybe we can compute L and R, maybe not. But they could all be different. Okay? So that's what we're saying. Okay, that's the main insight here, is that even without distributivity, maybe we can make sense of these things. And for example, this left solution here, this is exactly what BGP, this is the protocol that's running the global internet. It's the protocol that glues together all ISPs and all sort of large networks in the global internet. And it's essentially doing this without distributivity, without algebraic distributivity. Of course, so what we're saying here is we want to expand the notion of algebraic pathfinding so that, a subset of it is nice, well-behaved semirings that have this distributivity property, but we can expand that to account for these strange policy-rich routing protocols. And what do I mean by policy-rich? This is another way that routing protocols in the internet often lose distributivity, is we don't actually have link weights okay, in the internet. We have functions on the arcs. They're called route maps. If you've ever programmed a router from Cisco or Juniper or something, they're called route maps. And essentially, you take in a route from your neighbors, and you don't multiply it with something. You apply a function to it. Okay, and that function, in the most sort of abstract sense, looks kind of like a conditional thing. You look at, f of a is a is a route here, or a route weight, or some sort of representation of a path, and you look at it and you say, well, is P true of A, where P is some predicate? And if that's true, then well, you apply policy G. Otherwise, you apply policy H. So this is ubiquitous in internet routing, especially in interdomain routing. And you can sort of imagine that in this version of distributivity is something like this, that you can just push the F through the plus. You can just imagine that it's very hard to maintain. As a matter of fact, maintaining distributivity when you have these kind of route maps is nearly impossible. And this is, they're everywhere in the internet, okay? So, here's our solution. Like I said, we just say, okay, we have 3 different kinds of solutions, potentially. Of course, we're going to need some conditions on the algebraic structures to guarantee that we can compute these things, the left and the right. And we also want unique solutions for reasons that I won't go into, but one of the problems with the existing BGP protocol is that it's not guaranteed to have unique solutions. This causes all kinds of operational problems for internet service providers and the engineers that run these networks. They often have bugs, stable routings that they just can't understand, and it's because there aren't guaranteed unique solutions. So we want unique solutions, so we're going to have to impose some additional constraints. And here they are. So I'm kind of summarizing the output of about 15 years of research, right? It's been kind of simplified and simplified over the years. We started off with very complicated models, and they get simpler and simpler and simpler and simpler. One of the great things we discovered a couple of years ago was that Dijkstra's algorithm still works. As long as you have a total order, and it computes. What does it compute? What does Dijkstra's algorithm compute? It computes a right solution. So in other words, left solution is you get the best route given what your neighbors have. Okay. A right solution is basically you look at the neighbors of your destination, right, and you take their best routes to compute the next hop to the destination. That's what Dijkstra does. Okay. And it turns out, okay, what I mean by Dijkstra solves one row of this, okay, one row at a time. And we had this very complicated algorithm that was kind of like a greedy algorithm, very complicated. And we kept making it simpler, making it simpler, making it simpler. And then one day we looked at it and said, that's just Dijkstra's algorithm. The reason I initially didn't think Dijkstra's algorithm would work, because Dijkstra's algorithm is very sensitive, it's very fragile. It's easy to break it in various ways, like negative weights, for example. And so it was kind of a big surprise that Dijkstra's algorithm actually works. As long as we have this kind of sensible constraint that when you think of times now as something like, addition. It's the weight of your A times B is the weight of the path that has A and B in it, right? The weights A and B combined give you a weight, and that's always greater than or equal to the weight A. Okay, so in other words, you never extend a path and get a better weight. Well, it just seems like a pretty reasonable thing, okay? So that's all we need for Dijkstra, and what's nice about that is the proof is just proof by induction. No new mathematics required. N minus 1 steps of Dijkstra. Nice. This has been the really hard thing. Bellman-Ford. Why is Bellman-Ford difficult? It's because you can think of it's a matrix multiplication, but the problem is you know, when you do matrix multiplication with semirings, there's a measure that it's monotonic convergence. Either every entry stays the same or it gets better at each iteration. The problem with distributed Bellman-Ford without the distributivity rule, by the way, there's two uses of the word distributivity here, right? So I'm sorry, it's a little confusing. One is the algebraic rule of distribution of multiplication over plus, and the other is the sort of asynchronous distributed computation happening on multiple nodes, you know, that are communicating like routers do, okay? So without this algebraic distributivity, we need to say that this less than or equal to is now a strict less than. You know, we can't have that equality anymore. And we also, either the domain that we're computing over has to be finite, or we have to extend the routes with a path, the explicit path in the algorithm, and we eliminate routes with a loop in the path. Okay, so there are two ways to do it. So the reason, like I said, that this was so difficult is because it's a non-monotonic convergence. And we've had many, many different proofs over the years, and I think now, just in the last few months, we've come up with sort of the final proof that has nailed it to the wall. And it's based on modeling the convergence with an ultrametric. I don't know if you're, we take these matrices and we define an ultrametric between them, a sort of closeness between the matrices, because we can't do that pointwise. It has to be some sort of global measure on the matrix. And we show that that measure is going down so that there's convergence. If anyone is interested in that result, send me email, because I have a draft paper that we just submitted for publication. And it's probably, if you're interested in this area and would like to know more about like references, citations, things like that, this draft paper that I have is send me a link, send me a request. I'll send you the paper, and that you can sort of follow the citations in that paper, I think, or on my website. So that proof was very difficult. And like I said, we had many versions of it over the years. And this last one, what we did is we did it all within a theorem proving system. So one of these interactive theorem proving systems, because it was AGDA, you know the AGDA system. Okay, we did it inside the AGDA system because we had this proof many times, and every time we'd think we had the proof, we'd set it down, look at it again after a couple of weeks and find a bug. Right? And then we try to fix it, and then we try to fix it, and then so we did it in this theorem proving system because now we're unless the theorem prover has a bug in it, we're pretty sure we proved everything in the system, not a single assumption. And not only that, but we implemented a model of asynchronous distributed computation, and we showed that with this constraint, that no matter what state you start in an asynchronous computation with very weak notion of correctness, I mean, messages in this model of asynchronous computation, messages between nodes can get lost, corrupted, dropped, which is not the case with BGP, by the way. So this is a very weak computation model. We showed that no matter what state you start in, it will eventually converge to a unique solution. Okay, so that's all proved formally, and we're very happy about that. All the pieces seem to finally fit together. So it was the first time we actually were able to fit the asynchronous computation model, to fit it together with this non-classical convergent stuff. So that was very nice. Another result that I want to mention. Remember here, maybe Claudio will be interested in this. Remember I said here with a nice path algebra, there are n-1 iterations of the matrix equation. So we've had this open question for 15 years. Like, what is the, given these, if I have these If I throw away algebraic distributivity, and now I'm not going to do distributed computation, I'm just going to do this iterative thing, right? We know that it's going to converge. We have the proof that it's going to converge, but we never had a bound. How many iterations do we need? By the way, each iteration, each multiplication is like n cubed operations, matrix multiplication, right? But how many iterations do we need? It's kind of a measure of the expressiveness of the policy language or whatever. There were people that were claiming in the literature without proof that it's exponential. Okay. We recently proved, again, in the theorem prover, that actually, can anyone guess? Take a guess what it might be as a function of n. Turns out to be n squared. You can actually iterate n squared. We have an example that requires n squared iterations, and we have a proof that that's the maximum. For these kind of strange, exotic, policy-rich algebras, it's n squared. So that's kind of the basis. That's kind of what I wanted to talk about. I have an example here, but I'm not sure. I'm not sure. Do we have time to go through an example? We do have time. Yeah? Okay. So let's stop there for a minute before I go into the example. That's kind of the technical punchline, if you will, of this work, is that we can generalize semirings. We can throw away these precious rules. I mean, most mathematicians already think that semirings are really impoverished structures. They don't have much structure. So they're always surprised that we can do stuff with semirings. And here we are throwing out the two most important rules in the semiring world, and we're still actually showing that we can compute interesting things. And also, it's not just it's actually, this is happening in the real world. This is a model of how we could fix the protocol that runs the global internet. We could impose this constraint. That would be very difficult to do politically, but that's another story. Okay. So what I want to show you now, rather than, I want to show you an example where this theory, yeah. Turns out we can't use that. It turns out that trick you're thinking of depends on distributivity. Yeah. Too bad. So the standard trick is to, rather than iterating, what you do is you essentially you square it every time. You take the second power, then the fourth power, then the eighth power, and so on. The 16th power, and so on. And but that correctness depends on distributivity. Like most things, like almost everything breaks. Everything you ever knew and loved, breaks because of a lack of distributivity. Right? This is what's driven us absolutely crazy. Okay. Yeah, too bad. Doesn't work. Okay, so what I'm going to show you is an example that explains some anomalies that people kind of noticed but didn't really understand. And I'm going to explain them in terms of this theory. And it's kind of a simple example. We can build a semiring, which I'll call the widest shortest path semiring, and where the weights are distance and then capacity or bandwidth. And I'm going to compare these things lexicographically. Like I'm going to pick the shortest path, but if I have two routes with the same distance, then I'm going to break ties with the maximum capacity. I'm going to take the maximum capacity. So and it turns out it's, I'm doing some sort of lexicographic product of min plus and max min. And it turns out we can define a semiring. It's perfectly well defined. It has global optima. Here it is. Here's an example. Okay? This is the bottleneck link, okay, because it has distance 1, which is really good, but terrible bandwidth, terrible capacity, 10. Over here I have 100 and 90, 100 capacity, very large, okay? So this bottleneck is going to act a lot like that customer-provider link that I showed you in a certain funny way. Although this is a semiring, so there are global optimal paths here. And I'm going to look at the paths between 0 and 2. What are they? They're this path, okay, which has weight 3, 10, okay, and this path up there, okay, which has weight 3, 10, okay. But it turns out, so these are semirings. We should get global optima. But if we've ever used something like, if you've looked at a standard algorithms book and you look at Dijkstra's algorithm, right? You don't just compute the best weight. You also compute like the previous link or some way of keeping track of the path so that after you run the algorithm, you can reconstruct the paths. Okay? Well, it turns out that Dijkstra won't compute both of those paths. And it turns out also Bellman-Ford, if you look at standard algorithms for Bellman-Ford, you extend Bellman-Ford algorithm to keep track of the path. Turns out it won't compute both of those. Okay? So I won't look at this, but here are the optimal paths between 0 and 2 and 2 and 0. They're just symmetric paths. And here are the paths Dijkstra will compute. It doesn't compute one of the paths from 2 to 0. And Bellman-Ford is kind of the opposite. It doesn't compute one of the paths from 0 to 2. So let's see why that's true. Let's just intuit why that's true. Let's look at Bellman-Ford first. Bellman-Ford, you take the best routes that your neighbors have, and that's what you build on. What's the best route from this guy's perspective? It's 100. It doesn't use that link. So this guy, from his perspective, from Bellman-Ford, all it sees is one path from its neighbor. It doesn't see that link. So you won't compute it. Okay, what about Dijkstra in the other direction? Let's say from 2 to 0. Well, remember how Dijkstra works. It takes sort of it optimizes by building this tree, it's a greedy algorithm. The greedy algorithm won't take that link. It'll take that link there and then down to that link and then over to that link. So it'll miss that link as well. So, how can we understand this using the theory that I've given you? Here's how to do it. So what I'm going to do is I'm going to start from that original metric, distance, or I'm sorry, it's min plus with max min tiebreaker. Okay? And there's a complex algorithm. I mean, it's the algorithm plus these little extra computations we do to keep track of the paths. Okay. What I'm going to do is I'm going to take that computation out of the algorithm and put it in the algebra. Very simple. So I'm going to take a modified metric and a generic algorithm. My generic algorithm is always going to be matrix iteration. I don't really care about efficiency here. So the modified algorithm, what is the modified algorithm? Before I had shortest paths. Oh, there's a missing T there. Shortest paths, some sort of lexicographic product with widest paths. That's what I started with. Now I'm going to lex on the actual path. That's going to be part of my algebra now. Okay? This algebra is not distributive. Okay? Why? Well, it turns out it's not distributive because for a kind of a technical reason, it turns out because this algebra is not cancellative. So if I had, A times B, cancellative, I mean A times B is equal to A times C implies B is equal to C. That algebra is not cancellative, this part. And this lexicographic product requires cancellativity in order to preserve distributivity. So this thing is not distributive. So of course, globally optimal paths, remember what I've been saying, it's globally optimal paths might not be the same as what Bellman-Ford computes and what Dijkstra compute. These could all be different. Okay, and we saw that in this example. So it's a simple example. It's one that people have noticed in, well, in various ways, but didn't really have a good way of explaining it. We can just say, well, that algebra is not distributive. What do you expect? Okay. That's the end. That's the pun. That's the end. Yeah.
Can you show that little example where Dijkstra and Bellman-Ford don't compute everything that they were supposed to do? Yeah, this one. No, yeah, this is the one. Now, suppose that you have a tweak in your algorithm, that you choose a very small constant k, say 5, and then you compute the 5 best.
Yeah.
You probably could have good solutions practically. I mean, I'm not talking about algebra. I'm just saying in practice, right? Because, for example, you would consider those two alternatives there. If you compute the 2 best solutions.
Yeah.
K here is the K best solutions. That's what I'm suggesting.
Yes.
I don't know if this works, but intuitively, it seems to me that it would give good practical solutions to things.
But here's the thing. You can define semirings. So if I give you a semiring, you can define another semiring that given a k and a semiring, you can find a new semiring that computes the k best paths over that semiring.
Yeah.
Okay. You can certainly do that. And that might work here. Okay. But that's not the problem I'm trying to solve. That's all. I'm trying to solve a different problem. I'm trying to figure out when we can get exact, unique solutions to these matrix equations with policy-rich protocols. That's the problem I'm trying to solve. I don't want to change I want to keep the problem to be the one that exists in the internet. Yeah.
Okay. Thank you.
Mais perguntas? Maybe I have one.
Okay.
Did you manage to convince any of the engineers about your ideas?
Well, how many people are familiar with the IETF, the Internet Engineering Task Force, the one that produces all of the Internet standards and stuff? We have actually written what's called an RFC, or that's what their standard documents are called. We've written a informational one that explains why people are getting these multiple solutions, because that wasn't well understood by the operations community. And so when I was at AT&T, I actually saw these things happening in the real world, and they cause a huge amount of problems because the system can fall into a local optima, and you have to manually, get it back to where it should be. So in other words, the system can fall into an undesired stable state, and you have to manually get it back. The problem is that the internet service providers don't share their policies because they're considered to be proprietary. They have a lot of company-related information in them and this and that. And so a lot of times the interaction of these different policies in different companies interact in a way that causes these problems. So how do you debug a problem when there's no global knowledge? Right. And so that was what the RFC was about, explaining the problem and then saying, well, sometimes you need to communicate between the ISPs about your policies, because otherwise you're not going to be able to figure it out. Yeah. That's another reason why, in this case, we want unique solutions, because we want to make sure that you can actually debug routing problems.
Solutions only if they provide you their policies, right?
No, well, the thing is, if we could somehow manage to convince the world, the operators of the world, to impose this restriction on the policies, but the only difference is replace that B by a function applied to A. Because really, in the internet, these B's are not there. There are functions, those root maps that I talked about. If we could impose this restriction, and what's nice about this restriction is that it's invariant under root maps, right? If you have a language without root maps that obeys this, and you add root maps, this conditional stuff, it still obeys that. So that's really important. So it's really, this is the right, I mean, this is a really strong, works really well for policy-rich protocols, this constraint. If we could impose that on, right now there are no constraints like that on BGP. That's what the problem, that's where the problems arise. If we could impose that on the world, then we could eliminate these problems. The problem is, the interdomain routing world is very hard to make changes in that world. For example, everybody knows that BGP security of routes, is a really important problem. You can easily hijack routes in the interdomain world and do terrible things, and it happens occasionally. So there's an extension to BGP that has been defined and implemented by all of the vendors, the router vendors. It's been around for 15 years. It's never been deployed for political reasons. So the thing is, there are lots of problems in this domain, and it's very hard to get cooperation among the thousands of operators out there to fix problems. So security is the #1 problem today in interdomain routing. And this problem that I'm thinking about is maybe number 10 or 12 on their list. So imagine how hard it is to get them to impose something like that. But I think of it more now as kind of an abstract. What we're doing is we're just extending the semiring theory, and perhaps there are many other applications to that extension, not just routing in the internet, or maybe we can use it in future routing protocols, and so on. So I've kind of given up a little bit on the interdomain, fixing interdomain routing. It's too political. It's not a technical problem anymore. It's all politics. Yeah. Wait. Hold on for the microphone.
Is there an example where this condition fails? Some simple example to explain why I would have some roadmap that does not obey this condition.
Good example. Good question. Again, I'm sitting in that J node, if you remember that. This is a customer. I love customers. I hate I'm sorry, it's the other way around. I love customers. Okay, I hate providers. Okay, so now depending on which way the preference order goes, let's say that, in other words, I'm going to switch the actual order in the real. It's too bad the order in the real protocol goes the other way. It's the dual order, so I'm confused by that. But if you looked at that example that I showed on that slide, with the preferring that longer path through a customer, okay, it violates that rule if you get the orders straight in your mind.
I think about the number of hops, so maybe I prefer the longest path, and then the
yeah. That could be, you could do something like that, yeah. For example, with those route maps, you can do really crazy things, right? You can look at a route and say, it has 17 hops. I love the number 17. You can really do that, and people do things like that. So.
Okay, thanks.
Muito obrigado.
Ok, muito obrigado.